Just two problems here, 38 and 39, reading potential energy curves. I am not going to try to reproduce this sketch in this one. Instead, I'll just put my book right here. So here's this figure. Now remember, if you're just trying to go for like an intuitive understanding of what's going to happen here, you could imagine that there's like a little ball or skateboard or something there. So what would happen if you put it right there? Nothing would happen. If it already had some kinetic energy, then it would just keep going at a constant velocity in whichever direction it was already going in. And then when it got to here, then it would start to accelerate down to here, constant velocity over. Would it make it up to here? Well, if it started up here, it would, sure, because it's got enough energy, right, to get to there. And then it would come down here, and then it would get up. It couldn't get past this point. If you started with a constant velocity here, or sorry, a zero velocity here, then you could never get higher than this, because your total energy would just be that potential. Now, if you started here and you already had some kinetic energy, then maybe you would have enough to get up to here, maybe not. So anyway, that's a little overview. I think that last question about getting up to that top right part is part of the question. So let's see. We got a particle of mass 0.2 kilograms. I can travel only one-dimensional under the influence of a conservative force. The graph has these values, so they give us some scaling stuff there. The particle is released at the point where U forms a potential hill of height at 12 joules, which is that what the B? Yep. With kinetic energy 4. So it's released right at the top of that hill, and its total mechanical energy would be equal to its potential there at B plus its kinetic energy there at B. Now its potential, they're telling us, is 12 joules, and the kinetic energy is 1/2 mv squared. Oh, they're not, sorry, just kidding. With kinetic energy 4 joules, they just told us the kinetic energy. What's the speed of the particle at 3.5 meters and 6.5 meters? What's the position at the turning point on the right side and the left side? Okay, so the total mechanical energy is 16 joules. That is where we are at, right? So what's the speed of the particle at position x equals 3.5? Well, I'm looking at my graph here. I don't think I need to bring it over. At 3.5, the potential energy is at 9 joules. So the mechanical energy at x equals 3.5 meters is now, of course, the total mechanical energy is constant, right? Because there's only a conservative force here. So mechanical energy is conserved. So that means the total is still 16. And then looking at the graph, UA is 9 joules. So it looks like I'm going to have 7 joules of kinetic energy. So 1/2 mv at, we're at position A basically here, right? Because we're in that little flat bit. So I can reference that in the same way. So it looks like the velocity, excuse me, is going to be the square root of 14 divided by 0.2. Looks like it's going to be 8.4 meters per second. I think that looks all good. And at point B, the total mechanical energy is going to be equal to, now where are we at, 6.5. Total mechanical energy is conserved, it's still 16 joules. At 6.5, it looks like we've got no potential energy. So it's all going to be kinetic. So that's my 1/2 mv, let's see, what do we want to call that? I guess I could just call it 6.5 squared is equal to 16, the whole enchilada. So the speed there is the square root of 32 is 12.6 meters per second. In part C, they want to know what's the position of the turning point on the right side. Well, the turning point on the right side is however high up you get on this so that you get to 16 joules. Like all 16 joules would be kinetic, would be potential energy, sorry. The kinetic energy would be 0, and that's where it would turn around. The turnaround point, just like considerations in calculus class, the turnaround point is where the velocity is equal to 0. When the velocity is 0, it's all potential energy, all 16 joules of it. So let's see. C right here is at 20, that's at 24. It's not going to get up to there. We don't have enough energy to do that. We're only going to get up to wherever it's 16. B is at 12, so somewhere in between here and here, right? So I just need to figure out what's the equation for this, and I guess I'm going to assume that that is the point 70 and this is the point 824. It would be nice if they had the little dotted line thing here so that we could know for sure, because I need to figure out the slope of that line. What is the equation of that line? I'm just going to go with, well, I was going to say I was going to go with y's and x's, but I'm not going to. I'm going to go with u's and x's. So I know that this line goes through the point 7, 0, and I know that it has a slope of, let's see, rise is 24, and the run is 1, right? Yeah, I think so. So that's 24. Let's see, the rise is in joules and the run is in meters. So 24 joules per meter. Okay, so could I write an equation for that line? Sure. In point slope form, it would be y, but my y is actually u, right? Minus y is equal to the slope times x minus x. So we want to know where the turnaround point is. In other words, what's the x value when the potential energy is 16. So 16 is equal to 24 times x minus 7, and so it looks like x is going to be 7 2/3 meters. And then we'll play a similar game here with D. If this is, sorry, I should have said this earlier, as we go through this problem, if there are points where you start to understand what's happening, you should be pausing me and taking over yourself. Probably now would be like a time like that. So how about on the left side, when does it get up to 16 joules? Well, somewhere up on that line, it's not going to make it up to UC, which is 20 joules. We don't have that much energy. So I need to find the equation for this line that goes through. How about the point 1, 20, and it has a slope of negative, let's see, the rise is negative, it goes from C, negative 11, looks like, right, from 20 joules down to 9, so negative 11 over 2 with negative 5.5 joules per meter for the slope. Okay, so my equation this time is going to be u minus 20 is equal to negative 5.5 times x minus 1. And we want to find out where it's at, what's the x-coordinate when all of the energy is potential. So when that's 16. So that gives me negative 4 over negative 5.5 is equal to x minus 1. So x is going to be 1 and change. 1, 4, like about 1.73 meters. And that makes sense if you look at the graph. I like that answer. All right. How about 39? Got another graph, kind of similar. If all this is like made sense now, you should definitely pause here and try 39 your own self. So we got figure 848, which showing another graph of u versus x. We got a 9/10 of a kilogram particle this time. Non-conservative forces are not involved. What does that mean? It means that all the things that we think should be true here are true. No non-conservative forces, no friction, no things like tapping out energy from the system or adding energy in. Mechanical energy will remain constant, be conserved. 3 values are of the A, B, and C are 15, 35, and 45. Particles released at speed when the x is 4.5 meters, the speed is 7 meters per second, headed in the negative x direction. All right. If the particle can reach position 1, then what is its speed there? And if it cannot, what is its turning point? Okay. First thing we need to do, where is it released at? It's released at... So the total mechanical energy is the same for all points. So that means if it's released at position 4.5, then that is the total all the time. So how much potential energy does it have at 4.5? That's in that low spot at A. So that's 15 joules of potential. I'm just reading that out of the graph. And the kinetic energy, 1/2 mv squared there. When we do 1/2 mv squared, we're just interested in the speed, so we don't need that minus sign. Not that it matters. We've got squared off there anyway. So I got 15 plus 1/2 mv squared. So that's about 37 joules. That's what I'm getting there. That's the total mechanical energy. Okay, so does it have enough? UB is at 35 joules. So can it make it up to the 1 meter mark? Yes. And at the 1 meter mark, the 37 joules, 1 meter mark, and kinetic energy at the 1 meter mark. Well, the potential energy at the 1 meter mark, that's up on that little plateau where the potential energy is 35. So it's going to have 2 joules left over for kinetic energy. So that means I've got 1/2 mv at position 1 squared is equal to 2 joules. So let's see. So I'm getting that that's the velocity at position 1 is going to be about 2.1 meters per second. And it will be headed toward the left, right? It will continue because it had enough. You know, it's like if you're still thinking about that little marble skateboard, whatever, riding around on this ramp. So it had like a push here, right? It had some 7 meters per second. Was it enough to get up to here? Yes, because there were 2 joules left over to be kinetic energy up here. So it's cooking along here, slow it down, had enough to get to here, and then constant velocity as it moves to the left up there. What part was that? Is that just part E? A, I mean? Yes. I don't know why I said E there. That was weird. What are the magnitude and direction of the force on the particle as it begins to move to the left of 4 meters? Okay, so that's on that little slopey part. So I know that the derivative of this is the opposite of the force. So that means, of course, you could just move the negative sign to the other side. So I just need to find the slope of that and then switch the sign. It looks like the slope is, let's see, rise is that 15 to 35 is 20 over 2. So the slope of that is negative 10, but I'm going to switch the sign. So that is going to be 10 joules per meter. But do you know what joules per meter is? That's the same as newtons. So 10 newtons in the positive direction. I think that answers B and C. C was the direction, maybe. Yeah. Suppose instead the particle is headed in the positive x direction when it's released at 4.5 with the same, okay, so same thing, it's just going the other way. If the particle can reach x equals 7 meters, we know that it can't, right, because we already figured out the total energy. They're not changing that on us. What's its speed there, and if it cannot, what's its turning point? Okay, so the turning point, that's going to be like what we did in parts C and D of the last problem. The turning point is going to be where on that line do we have 37 joules? All potential. How high can we get? And that's the highest we can get if we use every single bit of our 37 joules. If we spend it all on potential energy and have 0 kinetic energy, that is our greatest position that we can get to. Okay, so let's see. It looks like this goes through the point, let's use 5, 15, and it looks like the slope is, I'm just finding the equation for this little bit right here. So that's point 515 right there. And then rise is, that's going from 15 to 45. That's 30 over 1. So that's 30. So if I wanted to write the equation for that, it would be u minus 15 is equal to 30 times x minus 5. And I want to know when that is 37, then what's the position? So 37 minus 15 is 22. That's not a hard math problem there. Divided by 30 equals x minus 5. So the position is going to be 5 and 22 thirtieths. Is that 0.73? 5.73. Let's see. 5 plus 22. No, 733. Over 30. 5.73. Yes. One of the things I said, I think, was right. 5.73 meters. And that makes sense with the graph, right? That seems like a reasonable answer. What are the magnitude and direction of the forces on the particle as it begins to move to the right? So same thing, just like we did in parts B and C here. The force is equal to, you can put the negative on either side of that equation because math. So what's the slope? Didn't we just figure that out? We did. It's 30, right? So the force is negative 30 newtons. I'm just going to flip to the back and make sure my answers for 39 are good. I forgot to print out the even answers for this one, so we're going to have to cross our fingers on that. I'll check them and then I'll come back and I'll comment in the video at the bottom or in the description of the video in case I made any mistakes. So if you don't see anything there, it means we are good. Let's see, 39, 2.1 meters per second. That sounds familiar, yep. 10 newtons, positive x direction, 5.7, 30 newtons. All right, all good. I bet we did 38 right, too.